In this video, we will discuss multi-objective particle swarm optimization algorithm, and we will try to understand this using different numerical examples. For example, you can see here first example we have training machine learning model. Second example we have here developing a fitness tracker. Then third example you can see here for buying a car, that numerically we will discuss step by step in detail. After that you can see here multi-objective PSO implementation steps. Consider a multi-objective optimization problem that step by step we will discuss, and here you can see different steps that step by step we will discuss. In this video we are going to learn about multi-objective optimization problems. First question is, what is multi-objective optimization? Objective optimization is also known as Pareto optimization. That is a field of decision making which deals with problem containing many objective function. Many objective function means that is more than one objective function to be optimized simultaneously. So we have here multiple objective function that need to be optimized simultaneously. As in the single optimization problems, there exists only one objective function and we need just one optimal solution. But in multi-objective optimization, our goal is to identify a set of solutions which optimally match multiple objectives. So here we need Pareto optimal solution. In multi-objective optimization, the goal is to identify a set of solutions which optimally match multiple objectives. And these solutions are called Pareto optimal solutions, or we can say non-dominated solutions. The next question is, what is Pareto optimal solution, or we can say what is non-dominated solution. So Pareto solution is one in which improving one objective function result in the loss of at least one of the other function. That we will discuss in more detail in the upcoming slides, that what is the difference between dominated solutions and non-dominated solution. When we will try to understand this using numerical example, we can clearly understand it. In simple words, we can say that optimizing the values generated by one or more objective functions affect the quality of the values generated by the other objective functions. Next, you can see here multi-objective optimization has a wide range of application. We can use multi-objective optimization in engineering design to optimize design of a product, or we can optimize multiple objectives like we can minimize cost, weight, or energy consumption. We can maximize the performance and other. We can also use this in economics. So we can create investment portfolios that maximize return on investments for certain level of risk. In finance, we can create loan rates model that consider the borrower reliability, loan amount, and interest rate. Last one we have in logistics, that we can use to optimize routes by reducing travel time and distance by considering different variables like traffic jams and the delivery time window. Now we will try to understand how optimizing for one objective function can have negative impact on the quality of another objective function. So we will try to understand this using a numerical example. So suppose you are training a machine learning model to recognize handwritten digits from 0 to 9. So we have here two main objectives to be optimized, that is speed and accuracy rate. For first one we have accuracy. For this, model should accurately recognize as many digits as possible. And second objective, here we have the model prediction should be fast and efficient. So for this we can use deeper models and train them on large data set and apply accuracy improving techniques, but this can lead to longer prediction time. So here the objectives can be conflicting. Now we will try to understand how optimizing one objective affects the another objective. First we'll focus on the accuracy rate, that is the handwritten digits accuracy rate. When we are focusing on accuracy, if you use different deep learning models with multiple layers and train it on large data set, this can result in very high accuracy rate in digit recognition, but the model size and the training time will increase. We need to fulfill both objectives, accuracy plus speed. But if you will just focus on the accuracy and use different deep learning models with multiple layers and use large data set, then it will be more time consuming. No matter if your accuracy rate is very high, it is 100% accurate, but it will affect the speed. It will take more time for the recognition. The second objective, we have speed. So if we prioritize speed only, then suppose you created a simple model with fewer layers and train it on smaller data set. So this may result in faster prediction, but the model accuracy will decrease. Your model can ignore some digits, or it can give you incorrect results, or it can misclassify. So we will get some errors if we just focus only on the speed. So we need to make a balance between both objectives. So multi-objective optimization can help to create a balance between these objectives. We can investigate multiple model designs, training data set, and optimization techniques that can maintain high level of accuracy while also maintaining the feasible prediction speed. And finally, we can choose one best model that meet our requirements. Second example you can see here. Now suppose you work for a company that make fitness trackers. So now when you are creating a new model, here we have two objectives: battery life, and second objective, that is its functionality. So to avoid the need for repeated charging, this tracker battery life should be long lasting. Second, we have this functionality. So trackers should include a number of features for monitoring health and fitness activities. We need to make a balance between both objectives. If you will focus only on the battery life, then it will affect its functionality. And if you will focus only on its functionality, then it will affect trackers, fitness tracker, battery life. So we need to make a proper balance between both objectives. So we have three methods that we can use to solve multi-objective optimization problems. First, we have constraint-based method. This strategy focuses on optimizing one objective function at a time. So it will optimize only one objective function at a time while keeping other objective function within certain constraints. Second, we have weighted sum method. This strategy weight each objective function separately. So if you have 4 objective function, this method will weight each objective function separately before combining them into a single objective function. The weight represents the estimated importance of the each objective function. Third one, we have evolutionary algorithms. So we know evolutionary algorithms are inspired by the natural selection. They operate by iterating a population of candidate solutions that are close to the Petro solution. So it will go through different iterations before giving the final solution. Now, question is which method is best? It depends on specific optimization problem you're trying to solve. Accordingly, you can use any technique. So right now we will use evolutionary algorithm. So we will use here particle swarm optimization algorithm. So we are using here multi-objective particle swarm optimization algorithm, and Particle swarm optimization we already discussed in previous videos. It is a popular meta-heuristic optimization technique that is inspired by the behavior of birds in real life. And to obtain a set of Pareto optimal solutions, we can further modify PSO for multi-objective optimization problems. So if you want to apply PSO to multi-objective optimization problem, we have to do certain modification. So different modifications are required here. First, introduce Pareto dominance. So we have to introduce the concept of dominance to handle multiple objectives. Second, we will keep the track of Pareto optimal solution discovered during search process. So second, we have external archive that we are using to keep records of Pareto optimal solutions discovered in each iteration during search process. Third one, to guide particles, select leader from the archive. So best solution we will select from the archive. As in the PSO, the agent's position is updated according to the best position and their own position. So to guide the particles, select the leader from the archive. And the last one, we will make sure the Pareto front has a variety of solution. So here fourth one, diversity preservation, that we are using here to make sure that the Pareto front has a variety of solutions. So we will do certain modification here in this PSO algorithm for multi-objective optimization problems. Now you can see our objective that we are going to use in multi-objective PSO. Suppose while buying a car, you have two objectives. First objective, we need the car at minimum cost. Second objective, we need maximum fuel efficiency. Now suppose we have 4 car options, car A, B, C and D, and here you can see its cost for each car and the fuel efficiency. For first car, we have the cost $10,000 and its fuel efficiency is 30 MPS, that is 10.62 km per liter. For car B, its cost we have $8,000 and its fuel efficiency 25 mpg. Car C cost we have $12,000 and fuel efficiency we have 35 mpg. For car D, we have cost $9,000 and the fuel efficiency we have 20 mpg. So first we will try to understand the concept of dominated solutions and the non-dominated solutions, because the concept of dominated and non-dominated solution are important for understanding how different solutions are compared in terms of multiple conflicting objectives in multi-objective optimization. That we will try to understand using this objective, using this numerical example. So now we will determine the dominated and the non-dominated solutions. So first we will compare car A. Here you can see the cost for this car we have $10,000 and the fuel efficiency it provide 30 mpg, that is 10.62 km per liter. Here you can see there is no car that is cheaper than 10,000 and offer more than 30 mpg. Here we have car C that offer more fuel efficiency, but this car cost is greater than car 1. So right now we have no car that is cheaper than car 1. So car A is a non-dominated solution. Second we have car B. Now we'll compare car B with other. The cost for car B we have $8,000 and the fuel efficiency we have 25 mpg, that is 8.85 km per liter. Here you can see there is no car cheaper than 8,000 that offer more fuel than 25 mpg. So this solution is also non-dominated solution. Third, we have car C. The cost for this we have $12,000. The fuel efficiency for this we have 35 mpg. That is 12.39 km per liter. So right now you can see there is no car cheaper than 12,000 that offer more than 35 mpg. So this solution is also non-dominated solution. Last one we have car D. The cost for this we have $9,000. The fuel efficiency for this we have 20 mpg. Now in this case, when we will compare this car with A, B and C, you can see car B, this one has less, that is $8,000, and it offer more fuel efficiency, that is 25 mpg. So this is a dominated solution. So car D is a dominated solution. This is dominated by car. So car D is dominated by car B. So now you can see we have dominated solution car D, and non-dominated solution we have car A, B and C. So now we can see the difference. Dominated solutions are best solution, but they are not good as comparison with other solution. So they are not preferred. So dominated solutions are not preferred because they are not optimal, because there exists at least one other solution that is better in one or more objective. So we will not consider dominated solution, we will consider the non-dominated solution because they are the best solution. They represent the best trade-off between multiple objectives. They are the Pareto front, they are efficient, optimal in terms of objective being considered. So therefore choosing non-dominated solution ensure that you are making the most efficient and effective choice. So here you can see the non-dominated solution A, B, C offer the best balance between cost and the fuel efficiency. So choosing any of these means you can't find another car that is better on one feature without being worse on other. And on the other hand, you can see this car D. So this car is not good choice because in comparison with this car we have another car that is car B. It is both cheaper and more fuel efficient than car D. So by focusing on the non-dominated solution, that is the Pareto front, we can guarantee that you are making the best possible choice. Now we'll try to understand how we can apply multi-objective PSO to find non-dominated solution. Like here you can see we want to minimize the car cost and we want to maximize its fuel efficiency. So first we will define the objective. Our objective, it's clear, we want to minimize the car cost and maximize its fuel efficiency. So we negate it because we want to maximize fuel efficiency, and PSO typically minimize the objectives. So we are using here the minus signs. We want to do here maximization, and for first objective we are doing the minimization, so there is no negative sign. So first we will initialize the parameter for this algorithm like population size, iterations, PSO parameters, C1, C2 constant and other. After that we will initialize the population for each particle randomly in the search space. Here each particle is considered car, and the range, that is the upper bound, lower bound, we have 5,000 to 20,000, that is $5,000 to $20,000. So randomly we will initialize the position for each car, that is a particle, each particle that is car in the search space. After that we will evaluate the objectives. We will minimize the cost. We have 10,000, 8,000, 12,000, and we will maximize the fuel efficiency -30, -20 and -35. You can see the basic features of multi-objective optimization. We need the optimal solution, objectives, either we want to minimize and maximize. Then we have different decision variables, and we can apply constraints. So according to your optimization problem, you can adjust the objective, decision variables and the constraints. So after that, we'll update the personal best solution. So we will update the personal best based on the dominance criteria. You can see the dominance criteria. Any particle xi dominate another particle xj if xi is less than or equal to xj and f2 is less than or equal to xj. Here f1 is the first objective function, f2 is the second objective function. We have different inequality constraints. So this dominance criteria should be satisfied. Then we will update the personal best. If the current position of xi dominate the personal best position, then update the personal best I to the current position of xi. After that, we will update the external archive. So add the non-dominatory solution to the archive and remove the dominated solutions from the archive. After that, we will perform leader selection, then update the velocity and the position for each particle according to the formulas. Then we will repeat the loop until the stopping criteria is met. So here you can see we modify the PSO algorithm for multi-objective optimization problems. So like that, you can do further more modifications in this algorithm. If you are working on any multi-objective optimization problem, you can modify accordingly and define your objective function and other. In this video, we just learned the difference between dominated and non-dominated solution, what is multi-objective optimization problem. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.